everyone. Today I'm going to talk about improve the JVM debugging mode based on OSR. Here's the agenda of today's talk. First, I will talk about debugging mode in JVM and why it's important and tricky for JIT compile code to work with the debugging mode. Then I will introduce two ways OpenJNI use to make JIT compile code supporting debug mode. And then I will show you some performance results and talk about future work. First, debugging mode in JVM. So when talking about debugging Java program, what first comes into your mind is probably debugger like Eclipse and Netbeans and GDB, etc. And those debuggers have debugging features. You can easily set breakpoints by just double-click any line in the Java source code to set breakpoints, or you can choose to inspect local variable values, or you can choose to watch field access and field modification. And as a JVM developer, we care about what's happening under the hood. And inside JVM, those debugging features are implemented through JVM tool interface. It's the lowest level of programming interface provided for the debugging tools. And JVM TI allow the debuggers to inspect the state of the running Java program and also even to be able to control the behavior of Java program. I will give you, here are some examples of the JVM TI interfaces. Like when the debugger wants to set a breakpoint, it's actually this JVM TI interface that's setting the breakpoint for the debugger. And when the debugger wants to inspect local variable values, it's get local long, get local int, and get a local object, and so on. That gets called to get the value of local variables. And when you want to turn on field watch to watch field access and modification, those are the JVM TI interface you want to call. So those are just a few examples. The entire JVM TI interfaces are pretty powerful. They provide a lot of other functionalities, like you can inspect the memory usage, or you can also manage, even do thread management through JVM TI. Those JVM TI can be called from native code, and the native code will be compiled into either dynamic library or static library, and we call those library JVM TI agents. So when in JVM, the debugging mode is triggered when loading the JVM TI agent, and upon JVM startup, before the actual Java application thread starts running, startup routine called agent unload will be called, and in this routine, the JVM TI agent will ask the VM for a bunch of debugging capabilities, like the ability to set breakpoints or do field watch, etc. So, and the VM will look at those capabilities and enable the corresponding hooks to enable those capabilities. And when JIT compiler starts, JIT compiler will check for the corresponding hooks, and if for some of them that are enabled, JIT compiler know that we need to compile the JIT code in a special mode to be able to support those hooks. Most of the debugging features is actually implemented on VM side. but we don't want the program to run in interpreter entirely, even for debugging mode, because we still care about performance of debugging mode. You can imagine if you set a breakpoint in your program and you need to wait for 10 times longer to even reach that breakpoint. So we don't want that happen. And also, we do have customers that really use debugging mode in their production environment, and we would like the performance. We don't want the performance to be very slow for those customers. And however, making compiled code working with debugging mode is not easy. I'll show you why. Here's a simple Java code snippet. It's just store one into the two int variables, and then increase one of the variable by one, and then add the two variables together and store into the third variable. And on the left-hand side is some pseudo bytecode that looks similar to what's going to be generated by Java-C. And notice that in interpreter, in the bytecode, the variable are represented by slots, by auto slots. So the auto 0, auto 1 there means the auto stack slot. And we can see that there's a mapping relationship between the Java program and what gets executed in the interpreter. So for each line in the Java code, there's corresponding several bytecode instructions. So debugging the Java code in interpreter is easy. Now let's look at the story on this compiler side. And we can, on the rightmost side is compiled code we could get by compiling the original Java method. And you can see that this compiler is smart and can be able to propagate all the constants and do the calculation. And so it's missing all the intermediate steps. So if we want to debug the original Java code, it's probably not a good idea to just read the compiled code. It won't give you the real state of the original Java code. So we need to find a way to be able to match the compiled code into the original Java code. Before I dive into the technique OpenGNI used to implement this, first we need to know a very important concept, that's yield point in our compiled code. In compiled code, yield points can be GC points and exception points. They are usually the points during executing compiled code. When it reaches those points, VM can take control of the execution at those points. Typical yield points could be just a normal function call. So at yield points, runtime can take control over the execution and do whatever it needs to do, like garbage collection, exception handling, and calling VM helper. And then after its job is done, it will give back the control to this compiled code. And in debugging mode, the debugging events are actually stop the word events, which means the VM needs to stop all the Java application from running. And for those threads running in compiled code, it needs to wait for the compiled code to reach a yield point. And then the debugging events will really happen on the runtime side. And then VM will decide to continue in interpreter and do whatever the debugger needs to do. So, our goal here is more clear that we want to be able to map the JIT execution to the interpreter execution only at those yield points. Now let's see how can OpenJ9 implement that. The first pretty naive way is through mimic interpreter frame shape. So for illustration purpose, I inserted two yield points into the Java code, and here's the compiled code that's generated from the Java code in mimic interpreter frame shape mode. You can see that in compiled code, the stack slots location are represented by symbols with types. And in mimic interpreter frame shape, the compiled code somehow matches the behavior of the Java code and interpreted code. And especially, mimic interpreter frame shape is very careful about the stores to the stack slot because it have to make the stack slot look exactly like the same like interpreter at yield points. If we execute the compiled code in mimic interpreter frame shape and the interpreted code side by side, you will see it more clearly that the method frame in the middle must contain the exactly same value at each yield point. So this restriction on the frame of method on the method frame makes it hard to enable optimization because we need to manually check all the optimization and make sure the stack shape, the method frame shape won't be changed because of the optimization. And even enable very simple optimizations like local common expression, local CSE, could be pretty tricky because the transformations can change the live range of variable, and then we can get very subtle bugs in GC. And because of those difficulties for mimic interpreter frame shape, many of the optimizations are disabled, and that give us pretty bad performance. And so we need a way to be able to map the JIT compiled code into interpreted code and want to not have so much limitations on the optimization. Here is where on-stack replacement will come into picture. And in OpenJ9, there's another debugging mode that's based on on-stack replacement, and we call it full-speed debug because it's much faster than the mimic interpreter frame shape version. In the debugging, the full-speed debug is run in OSR mode called an involuntary OSR, and it's because the OSR will happen at yield point, and when the debugging event happens, and the runtime will request for OSR if the debugging event do get triggered, and then continue in interpreter. So the timing of the OSR transition is totally decided on runtime. So that's why we call this involuntary OSR. And this is in contrast with another OSR mode called voluntary OSR, where the compiled code will request for OSR voluntarily. And this mode is used mostly for implementing bytecode instrumentation for handling the invalidated code path. Now let's look at an example of OSR translation in debug mode. So on the right-hand side is a compiled code that could be generated in full-speed debugging mode. The compiled code is able to do things that are more flexible, like it can put a variable into a register rather than store it directly onto the stack. And it can delay all the storing to the stack slots until it has to. So in full-speed debug mode, we don't need to carefully maintain the method frame exactly as interpreter. It's only when the debugging event that actually happens that we need to do that. So let's assume that we come to a yield point when calling the full function the second time. So if the debugging event is triggered, the cheat code needs to get out of execution and execute some transition code that will look into some kind of mapping and figure out which value to write into the method frame so that the method frame will look exactly like what it would look like in interpreter. And after the transition code fill in the method frame, as expected, the interpreter is able to continue with that method frame because the values are exactly what interpreter expected. And we can see from this transition that the most important part of the OSR transition is the OSR mapping, which the mapping will enable us to correspond the compiled code to the interpreted code. When we design OSR mapping, we usually need to take the following aspects into considerations. We need to be able to reconstruct the state of inline calls, and which means if the OSR transition happens in the inline method, we should be able to reconstruct the method frame of the inline method and also its caller. And the second aspect is we need to make sure the optimization don't validate those OSR mapping. So if a transformation do change the mapping, we need to update and maintain the OSR mapping. Also, the mapping should be cheap to update and maintain. And in OpenGNI, the OSR mapping is represented by the intermediate representation. So here the deep blue box is the normal basic block in a Java program. And the light blue box is the translation block that contains the OSR mapping. And inside the translation block, there are a bunch of IR stores into the auto stack slots. And on the right-hand side of the store contains uses of the symbol in JIT compiled code. So for simplicity, now we can just assume the store are to the interpreter stack slots directly. And in this way, because the OSR mapping is represented as IR, so there's no fundamental difference between those IRs and the original IRs in the method. So when optimization through transformation is able to take into those stores and uses automatically into consideration as part of the transformation. And guarantee that the transformation will, if the transformation change the mapping, the optimization will also update the mapping as part of the optimization. So in this way, our optimization don't need a lot of changes to be able to support this OSR mapping. If we put the translation block into a larger picture, here's a control flow graph for a simple method with one inline method. And again, the dark blue box means the original basic blocks in the original method, and the light blue box are the translation blocks. So there is the one translation block per method, and all the inline callees and callers all have their own basic blocks, all have their own translation blocks. And inline call handling is easy. We just need to link the callee's translation block into the caller, so that if the OSR translation happens in the callee, the translation block of the callee will be able to reconstruct the frame of the callee, and then it will go to its caller's translation block and rebuild the method frame for the caller as well, and it goes on until it reaches the outermost method frame and reconstruct the entire call chain. OSR itself is treated as an exception, so whenever there's any OSR point in one basic block, there will be an exception edge connecting that basic block to the method's translation block. And this idea of treating the OSR translation as exception is pretty neat, because in this way, one basic block can contain several OSR translation points, and we don't need to split the basic blocks and disrupt a lot of optimization that would only work on basic blocks. And analysis like live range analysis, reaching definition, still needs to treat those exception edges conservatively to guarantee correctness. And this is the intermediate representation part of the OSR infrastructure. And there's actually another part that we need to use side data structure. Remember I mentioned the symbols in JIT compiled code have types. So for a single stack slot on the interpreter side, JIT compiled code might have two symbols, one for address type stack slots and one for primitive types. So we need a way to figure out which symbols in the JIT method frame we need to write to the corresponding interpreter stack slots. And this information can be get from doing OSR live range analysis right after ILGen. Because after ILGen, there's no optimization kicked in yet. So the liveness at this point in the program will represent the liveness in interpreter. So we will know that at a certain byte code, which JIT symbol is alive and should be right to the interpreter method frame. And because the liveness represents the state in interpreter, we don't need to update the liveness information anymore. And so it's not affected by the later optimization. And runtime helper will look at the side data structure at runtime and copy the right value. And remember I said for simplicity, we assumed that the the IR stores in the translation block are all writing to the interpreter method frame directly, and it's actually hide an intermediate step. We are actually writing the value on the JIT method frame to a buffer first. So in the translation block, we first write the symbol values into a buffer, and then when this step, the step writing the values into the buffer is the same for all the translations, but it's the second part that's different when we transition from different instructions. In this case, for example, because the side data structure shows that at instruction 4, we should write the value of symbol 0 into the auto slot. And when we get to instruction 10, it's the value of symbol 1 that should be written into the interpreter stack slot. So this is the whole picture of our OSR representation, and the translation blocks are represented by an intermediate representation, and we need to use side data structure to manage the many-to-one mapping relationship. So now if we go back to the aspects we need to consider when design an OSR mapping, we can see that our OSR representation is able to meet all those requirements. It's able to reconstruct the state for inline calls, and because it's part of, for the intermediate representation part, because it's part of the intermediate representation, optimization optimization will update the mapping automatically, and also for the site data structure, because it represents the states in the interpreter, the liveness in the interpreter. It won't be changed by the optimization. And because the IR representation is just part of each optimization, so it's easy to update, and the site data structure doesn't need any maintain or update at all. So this is the overall infrastructure in OMR, and in FSD, so we use OSR mainly to get the program out of the optimized version of this code, which doesn't really represent what exactly happened in the Java code. So when the debugging event happens and we OSR out from the optimized version of the JIT, the runtime can choose to continue in interpreter, like in the case of single stepping, the program will stay in interpreter. And also the VM can choose to execute a different version of JIT compiled code after we OSR out from the original version. In the case of field watch, for example, the original compilation will assume that there's no need to report field access, and will not include the helper call to report the field access. And if the field watch is enabled, we need to get out from the original version that doesn't report the field access, and execute in a different version that will contain the call to the VM helper to report the field access. So the gist of the OSR transition is in FSD that we want to delay the overhead of debugging as late as possible and let the program run in a faster mode. And when the debugging events do get triggered, that's the time we need to get out from the optimized version and execute in a slow version that can reflect what exactly happened in JIT compiled code. And the performance improvements we did for full-scale debugging is mostly making use of the OSR infrastructure and do patching or recompile. But there's an interesting item that we did that's a little bit special. It's a new liveness we did for method entry initialization. We all know that both in debugging mode and non-debugging mode, the method entry initialization are very expensive. However, we need to initialize some of the variable at method entry because for an address type of variable, if it appears to be alive at a method entry and it's not initialized when the GC sees the variable as live and it's not initialized, the GC will crash because of the uninitialized value. So that means as long as there's a yield point between the method entry and the first use of the variable, we need to insert zero initialization. And this won't be a problem for non-debugging mode program because this situation is pretty rare. However, it becomes a problem for the debugging program, for debugging mode. Remember the uses in the translation block, and those uses are considered, can make the variable alive because of those uses. So as long as there's a yield point between the first use of the variable and the method entry, this variable will appear to be alive at method entry. And it becomes so common that we're actually zero initialize all the address type variables. And this can cause us great overhead. And the frustration is that the uses in OSR translation block are actually fake uses. They are not real use in the original program, and they only happen if the OSR really happens. So what we want to do is that we don't want to use the fake uses for liveness analysis. We want to use the real uses. And the real uses here is actually what gets used if the method were executed in interpreter mode. So again, we use live range analysis right after LGen to find out the state in the interpreter. And in this simple example, we can see that at this yield point in live range analysis, we'll find out that symbol 0 is actually live at that point, and symbol 1 is actually dead at that yield point. And then when we do liveness analysis for method entry initialization, we only consider the real uses in the original JIT program and the real uses in the interpreter program, but we won't consider the uses in the translation block, which are the fake uses. So in this way, the variable that appear to be alive because of the OSR uses will be able to be ignored. And if OSR do happen at those 0 points, the runtime helper will be able to figure out which variable is actually dead and hasn't been initialized. And then the runtime helper will look into the metadata structure we got from live range analysis and zero out the variable when the OSR transition actually happens. So in this way, we can lazily zero out the variables until we really have to, and instead of eagerly just zero it out in the main code path, in a critical code path. So after talking about the overall OSR infrastructure and the performance improvement we did, now it's time to look at the performance results. So here are some numbers we got from running DayTrader and some other benchmarks from SpecGVM 2008. And the bars are scores that normalize to the performance of Mimic interpreter frame shape. We can see that in most of the cases, full speed debug based on OSR can have around 40% or more improvement upon compared with Mimic interpreter frame shape. Now I'll talk about future work. This is an example of how OpenJ9 use the OSR infrastructure to implement debugging mode. And there are still actually some Java-ness components in the OMR level that prevent other sub-projects from using the same OSR infrastructure to implement their debugging mode. So we still need to do some refactoring work to strip out the Java-ness components from the OSR infrastructure. Also, there's always room for better performance because currently there's still about 40 to 30% gap between the debugging mode and non-debugging mode version. We can always try to improve that as well. Yeah, that's my talk. If you have any questions.
Two questions. In your performance chart, can you talk about how much, I guess, the FSD OSR-based mechanism compares to just default without?
You mean default without debugging mode? It's about. So the question is, what is the performance of debugging, full-speed debugging mode compared to non-debugging mode? It's about 40 to 30% less than the non-debugging mode.
And my second question, if you go back to where you first introduced, that intermediate buffer where we copy in the transition block workflow, you were saying that it was used for the kind of multi-to-one mapping of the slot. But I don't fully get why you, on the left-hand side where you have the existing JIT method frame, why you need to copy it into a buffer. Can you talk about that aspect?
And that part is more for for runtime execution. We are able to copy it into a buffer and pass it to some native code, and then the native code will be able to process this buffer, and then will give the buffer back to interpreter, and then runtime will copy the value from those buffer into their stack slot.
So the point here then is, if I understand you correctly, the buffer is in a specific format that the native buffer.
Yeah, we'll be able to understand. Yeah, so that we don't need to know the exact address of the interpreter directly.
It also decouples the internal details of the VM interpreter frame from the transition, right? The only thing that's transitioning is the data. The layout of the data is the interpreter, maybe subjects change and the interpreter developers develop the interpreter. You don't want to have to do lockstep changes into the runtime transition mechanism. So by having a buffer with a common format that's agreed between the two components, both components are free to change the internal, how they get to that buffer. You don't have to reach inside each other to switch.
So you said you can, so you're running in JDID code, also with many optimizations enabled debug, and then you can OSR into interpreted code, and then possibly the user can enable the field wash, and then you can go back to compile code.
Yeah, so we will decompile an OSR out first, and if new methods gets called from those interpreted methods, we can still call back to the GTID version. And by that time, the GTID version should have the correct information the user needs.
I have two questions. The first is, when was FSD full-speed debugging? When was that first released? Like when, I'm assuming before that, all we had was mimic stat frame. So at some point in time, we came out with FSD, the original FSD. When did that happen approximately?
The implementation. The question is, when was FSD first implemented? So the implementation and the infrastructure has been there for a few years, but before we always alias mimic interpreter and FSD. So the debugging mode by default is in mimic interpreter.
So when did it?
When did it get this alias?
Yeah.
Probably last year.
Okay. So like this, all of this stuff has just been like a multi-year.
It's many years. Yeah.
Okay. Who started it?
So the question is, who started working on full-speed debugging? I think the infrastructure, the OSR infrastructure, was implemented by DJ a few years ago.
Just curious if you have a perspective on how our technology compares with our competitors in this space. I'm curious how one or other VM implementations perform.
That information. So the question is, have we ever compared our performance of full-speed debugging with a similar product, with competitors' product? The answer is not yet. we will get to there. Okay, that's all.